One of the key ideas we really need to understand before we start getting into analysis and asymptotic notation is the idea of runtime cases. With this linear search algorithm, for example, we discussed the idea that, as the input size increases, likely something happens with the actual runtime itself. It may increase proportionally, it may stay constant, and we want to understand how that is changing. So based on that input size, how is the actual runtime changing? This is really just one side of the picture, though. It turns out that actually the runtime for this algorithm and many algorithms differs based on the actual input itself, not just the size of it. So let me give you an example. If we take a look at this linear search, suppose that you have the following list of values, and you wanted to search for the value, say, x equals 1. If you wanted to search for this value, it's the first value in the list. So what will happen is we'll go into the code, we'll start our iteration, we check to see if the value is the one we're looking for. It is, so found becomes true, and then we exit the loop. So this only took a single iteration, right? And for that matter, no matter how big this list is, if we were searching for the first value inside of it, it would always just consistently take that single iteration. We would call this constant time. It's constant time, meaning that no matter how big our input is, it always takes the same amount of time to execute. So the amount of time to execute doesn't scale based on the actual input size itself. It actually just remains constant because you always find it at the beginning of the list. So this is one situation that we could have. There are other situations, though. We could have the exact same list, and we could be searching for the last value in the list. In this case, we would have to iterate through the whole list in order to find the value. That would take about n operations, right? Where n is the size of the list. So do you see how there's a drastic difference between these two cases? If the value is at the beginning of the list, then it takes constant time. It's very fast, right? But if the value is at the end of the list, then it takes n operations. It actually grows linearly. And we could graph these out to see the actual difference between them, right? In the case where the thing is at the front of the list, it's just like this flat line, right? It doesn't change based on the input size. If this here is the input size and this here is the number of operations, we just have a flat line. It always takes the same number of operations no matter what the input size is. In the worst case, where the value is at the end of the list, we have this linear growth, right? So it actually grows like this linearly. As the input size increases, the number of operations proportionally increases linearly with it, right? Because we have n operations that are being run. And then there's this sort of idea of an average, right? In some cases, maybe it will be in the middle, maybe it will be at the beginning, maybe it will be at the end. We could ask, what happens on average with this particular algorithm, right? So those are the three things that we really need to consider. We want to understand for most algorithms what happens in the best case, what happens in the worst case, and what happens in the average case. Those are the three cases that we usually want to consider. And sometimes these three cases are all the same as each other. In some of the examples where we saw, a for loop that always iterated through the whole list, in that case, the best, worst, and average case were all the same as each other. But in a lot of cases, they won't be the same as each other. So we want to consider these ideas. Now, even though we have these three cases, in a lot of algorithms courses, we focus on one particular case, which is the worst case. The reason why we care about the worst case most is because it guarantees our runtime. If we know how something performs in the worst case, we know that, at worst, it will be a certain level of runtime, and then we could assume that we're either that bad or better, right? Whereas if we were to take a look at the best case, for instance, it would only tell us like maybe a small portion of how the runtime actually works. So generally, we take a look at the worst case. We may look at best and average case when it's actually relevant to the problem, say it's like the main differentiating factor between two very similar algorithms, or maybe the best case comes up really frequently, we may care about that, but generally we're going to focus in on this worst case. And I bring this up because this is going to be the core of asymptotic notation, is that we're going to consider these three pieces and show how we can actually analyze an algorithm based on these three cases themselves. So the main key takeaways here is that most algorithms are going to differ based on the input size, right? The size of the input itself, but also the inputs in general. Different inputs may give us different runtimes. We want to consider what happens in the best case, the worst case, and the average case. So let's dive a bit more into that in the next few videos. Thanks so much for watching, and I'll see you in the next one.